Hi, and welcome to a lecture on mutual coupling, where in this lecture we'll be concentrating on the transmit case, and this will also serve as an introduction to mutual coupling, at least as it applies to antenna arrays. So to begin, let's consider this scenario shown on the left, which shows an antenna with voltage V sub 1 applied across the terminals and current I sub 1 into the terminals. And note that although this is shown as a dipole here, this could really be any type of antenna. I'm just drawing it as a dipole, but at the moment the theory is applicable to any type of antenna. Here we can define an impedance Z sub 1, which as usual is the ratio of a voltage to a current. So here V sub 1 divided by I sub 1. And in this scenario, this is just the self-impedance. This is sometimes indicated as Z sub 1, for reasons that will become apparent later in this lecture. In other lectures, we may have referred to this as Z sub A. In any event, we're talking about the self-impedance, that is, the ratio of voltage to current at the antenna terminals when there's nothing else but this one antenna in the entire universe. And just to bring some reality to this, the self-impedance of a half-wave dipole, you already know to be 73 plus J 42.5 ohms, at least at the frequency at which a dipole is a half wavelength long. Okay, next, what about this scenario, where we have that same antenna, again, not necessarily a dipole, but now we have a second antenna, and with its associated voltage V2 and its associated terminal current I2. And now we ask ourselves again, what is this impedance Z sub 1 looking into the first dipole, so the ratio of V sub 1 to I sub 1? Well, this definition holds, but note that this will no longer be the self-impedance of a single dipole. This should stand to reason simply because we know that there should be some electromagnetic interaction between these two antennas. We sometimes refer to this electromagnetic interaction as mutual coupling. So mutual coupling between the two antennas will result in the ratio of voltage to current on any one of the antenna terminals to be different from the self-impedance. So now, assuming linearity, time invariance, and so on, we can establish a simple relationship between the voltages and the currents between these two antennas. And that relationship looks like this. It should be familiar to you. V sub 1 is a linear combination of the currents I sub 1 and I sub 2, and those combining coefficients are Z sub 1, at the moment just a coefficient, but we'll see this is the same Z sub 1 we talked about before, and Z sub 2. And similarly, V sub 2 can be written as a linear combination of the currents I sub 1 and I sub 2, where the combining coefficients are Z sub 1, just to give it a name, and Z sub 2, just to give it a name. So now with just some simple mathematical analysis, we see that, for example, if we set I2 equal to 0, then we get V sub 1 divided by I sub 1. So that makes sense. That's consistent with our definition of self-impedance before. And similarly, when we set I sub 1 equal to 0, we find that Z sub 2 from the equations above give us V sub 2 over I sub 2, which, again, is consistent with our definition of the self-impedance for the second antenna. Now what's interesting here is that we now have these two other coefficients, Z sub 2 and Z sub 1. So just to look at one of these, say Z sub 2, we see that Z sub 2 is the ratio of V1 to I2 when I1 equals 0. In other words, we make I1 equal to 0. You might say we're open circuiting that antenna and making it impossible for terminal current to flow. And in that case, Z sub 2 is the voltage on antenna 1 due to the current on antenna 2. And we have a similar definition for Z sub 1, using the same simple mathematical consideration. And these two factors, Z sub 2 and Z sub 1, we refer to as mutual impedances. So Z sub 1, Z sub 2 are self-impedances. Z sub 2 and Z sub 1 talk about the relationship between the two antennas. We call them mutual impedances. So you could now ask the question, what really, that is physically, is Z sub 1, 2 or Z sub 2, 1? What are mutual impedances? Well, if we just look at Z sub 1, 2 above, we established that that is a case where I sub 1 is 0, that is, that first antenna is open circuited. I sub 2 is something other than 0. In that case, the second antenna here is radiating, and it's radiating and resulting in an open circuit potential on the first antenna. So we see that in this case, V sub 1, at least according to the scenario, is the open circuit potential induced in antenna 1 due to the field that's radiated as a result of I2 being non-zero on the second antenna. So this is simply an interpretation of the mathematical definition that we found above. So now we see that to evaluate this mutual impedance, we would need to know what V1 is in response to I2. Well, we already know something about this. If antenna 1 is in the far field of antenna 2, then we know exactly how to do that problem. In other words, we know how to find the open circuit voltage of an antenna that's in the far field of some other radiating antenna. Because that other radiating antenna creates an electric field, we'll call it E super I, and we know how to find the potential induced. That's just E super I evaluated at antenna 1, dot product with the effective length. So that was the topic of another lecture. So we could use this procedure. We could set some value of I2 that's non-zero. That would result in non-zero E super I. We could establish the voltage in response to that current, and that would give us everything we need to compute the mutual impedance Z sub 1, 2. Now, the problem, of course, in an antenna array is that these two antennas are close together. They're not in the far field of each other, and in that case, we need to come up with something that's a little bit more general. In other words, we can't really use this effective length formalism because that depended on a plane wave illumination of the antenna for which we're computing the open circuit potential. So that's going to be a topic for another lecture, but you can see that there's certainly a way to do it, right? We just need to generalize this idea here so that we can find the open circuit potential when the instant electric field is not necessarily a plane wave. Suffice it to say, if we can get the open circuit potential in response to a non-zero current on the second antenna, then we have everything we need to get Z sub 1, 2. So there's a path to do that. And similarly, if we can get the open circuit potential on the second antenna in response to a non-zero current on the first antenna, then we can find Z sub 2, 1. Sometimes expressions for Z sub 1, 2 and Z sub 2, 1 directly in terms of the materials and geometry are available. In other words, in some cases, you can do this problem once and you'll find that things are independent of the applied currents and response voltages, as they typically are for impedances. So, for example, for thin dipoles, expressions exist that give you these mutual impedances directly in terms of the materials and the geometry of the problem. Because someone has already gone to the work of doing this experiment, at least mathematically, and then, of course, the response voltages and the stimulus currents disappear in the equations, and you're left with expressions in terms of materials and geometry. More often, these equations do not exist, and in that case, you need something called a full wave solver, something that can attack the problem directly using Maxwell's equations from square one. And in that case, then you could use a full wave solver to find the open circuit voltages in response to any set of stimulus currents, and in that manner get the mutual impedances simply by dividing one by the other. Suffice it to say, there is a subproblem here where we're trying to find the mutual impedances, and there are multiple paths. Some cases you have equations to do that, relatively few cases, again, primarily thin dipoles, but in general, you could consider using a full wave solver to find voltages in response to currents and thereby get mutual impedances. All of this generalizes straightforwardly if you have more than two antennas, right? Because we could simply take those same equations and expand them out to account for a third current on a third antenna and the associated mutual impedance here and here. So the dimensionality of these equations just expands. And you can do the normal trick of recasting this as a linear algebraic structure where we have a column vector of voltages, in this case n by 1, where n is the number of antennas, and a matrix of impedances, which is n by n, and a column vector of currents, which is n by 1. So you can compactly write this whole thing as the column vector V equals the impedance matrix, right, multiplied by the column vector of currents. If an array is transmitting, then we might want the currents in response to applied voltage. See, this equation tells us how to get the voltages if we know what the currents are. But for transmitting, it might be that we've applied a voltage and we want to know what the currents are, and from the currents then we could figure out how the radiation works. And from the radiation we could get directivity, total radiated power, and so on. So that's of interest. In principle, this is no problem, right? You simply solve the matrix equation for I, and that simply requires you to compute the inverse of the impedance matrix, and then you right multiply it by the column vector of voltages. But of course there's a catch, and you need to be aware of this catch or you're likely to generate misleading results. So here's the pitfall. You don't necessarily have control directly of the V sub n's, in other words, what we're calling the applied voltages. Typically what you have is a transmitter. And the transmitter can probably be modeled as a Thevenin model, where we have a voltage source in series with its impedance. So in that case, then, we have this circuit, which is a thing that we can control, and it's driving one terminal on the antenna array, and the impedance that we see at that one terminal, Z sub n, which is always the voltage at that antenna terminal divided by the current at that antenna terminal. Well, this would all be simple enough if we had just that one antenna, but here we know that Z sub n will not necessarily be the self-impedance of that antenna. Instead, Z sub n will be something more complicated because the other antennas will contribute to this impedance. So here, this is the active impedance, is one word for what we have here, or the driving point impedance. The active impedance, or the driving point impedance, or the driving impedance, all refer to the same idea, that is the ratio of voltage to current when you actually have currents on the other antennas and they are changing this ratio of voltage to current on the terminals of interest. Okay, so now you have this Thevenin equivalent circuit on the left, and then you have the current running through this impedance, the active impedance. So now the relationship between the applied voltage and the voltage that you may have set your transmitter to generate is going to be different. And they're going to be different according to a voltage divider. And that voltage divider is simply V sub n, the active impedance, divided by the sum of the impedances, that is, the sum of the source impedance of the generator and the active impedance at those antenna terminals. So there's some additional complexity here that we have to account for. Now further, typically a transmitter would be designed to have a standard impedance. So this impedance here, Z sub s indexed to n, would typically have some standard impedance, maybe 50 ohms, maybe 75 ohms, maybe some other number. But in general, this is going to be something which is set to be convenient for the designer or the developer of the transmitter and not necessarily appropriate for this active impedance. So here's where a lot of the complexity in mutual coupling analysis comes in. So just to say a little bit more about what this active impedance looks like, again, we could take the two antenna example where the voltage on antenna 1 is given by the linear combination of currents I1 and I2, combining factors consisting of a self-impedance and a mutual impedance. And then we could take this and divide the whole thing by I1. And that would give us the active impedance on that first antenna. So by dividing through by I1, we see that we have that the active impedance is the sum of the self-impedance and a factor, which consists of the mutual impedance multiplied by the ratio of currents, I2 over I1. So we see right away that this active impedance is not a conventional impedance, which is independent of the stimulus. Rather, the active impedance depends on the stimulus. It depends on the currents. So there's no way to write Z sub 1 which does not require knowledge of the currents on each one of the antenna terminals. So this certainly complicates the problem. Nevertheless, you can imagine a way to work this problem, right? A way to do the design problem even when the mutual impedances are non-zero. That is, even when you have mutual coupling. And here's the approach that you might consider taking. You might start off with the currents that give you the desired pattern directivity, right? You might start at the end and say, I want a certain pattern, a certain directivity, and currents in the absence of mutual coupling, I, would give me that particular pattern or directivity. And then you could incorporate the mutual coupling by using the equation V equals impedance matrix, right, multiplied by currents. And that would give you the applied, what we've been calling the applied voltages. Then in step 3, you could find the active impedance. That's simply using the expression that we already came up with. It's going to be the self-impedance plus the sum of terms, which depend on both mutual impedances and the currents on those antennas. That would give you the active impedance for each one of the antennas. And then you could solve for the source voltages in the Thevenin equivalent model, given those applied voltages. So now you know what to tell the transmitter. So that is a perfectly reasonable and valid thing to do, but I'll tell you that it's almost never done this way. And there's a couple reasons for that. The first reason is, typically you want these active impedances to be as close as possible to the source impedance conjugate for maximum power transfer. In other words, we know that if we want to maximize power transfer from the transmitter to the terminal in this antenna array, we're going to want conjugate matching. We're going to want Z sub n for that terminal to be as close as possible to the conjugate of the source impedance for the transmitter. So, as we just mentioned, the source impedance for the transmitter is likely to be fixed for the convenience of developing the transmitter. So, as a result, the active impedance should be fixed. So, typically, there is a lot of effort put into making the active impedances to be a fixed value consistent with this criterion. But you have another consideration. It's not just that you want maximum power transfer, but also you want to minimize reflection. And in order to minimize reflection, you don't want conjugate matching, you want those impedances to be equal. So if you want both of these things to be true, in other words, maximum power transfer requiring conjugate matching and minimum reflection requiring equal impedances, then you're going to want a real valued active impedance. Then we're going to turn out to have that the source voltages, as the voltages in the Thevenin equivalent model for the source, are going to turn out to be twice the applied voltages. So steps 3 and 4 above are not going to be necessary if these conditions are true. These two conditions above, we're trying to achieve maximum power transfer and minimize reflection. So in that case, we could assume that if this all went well, then things get a lot simpler and you don't actually need to do steps 3 and 4. Of course, that's never going to be the case, but it is a goal, and it's a common design goal in these development efforts. Furthermore, it's common that the mutual impedances are not known well enough for the above procedure to yield accurate values for setting those source voltages. And the reason is because for anything but the most simple arrays, say arrays of simple thin dipoles, you're going to probably require some sort of full wave solver, some electromagnetic simulation software that can tell you what the mutual impedances are going to be. Even that is going to require considerable effort to do those simulations correctly. There are always trade-offs between computational accuracy and computation time and so on. So we find that both EM analysis and measurement, even if you were to go out and measure this, it's hard to get impedances which are accurate enough to do this procedure well. So it is typical, in fact almost always the case, that you end up with approximate values for these impedances. And if you have only approximate values, then this procedure is a little bit less attractive because it really requires or presumes that these values are accurate. So a more common approach is to do something like this. Step 1. Design the arrays to have active impedances that are close as possible to constant real valued impedances. I call them Z0 here, but that are real valued and equal to the source impedances. All right? So a common thing to do in the first step would be to try to make the active impedances as close as possible to 50 ohms, for example, regardless of what the currents turn out to be for whatever direction you're going to point beams in, for example. Right? And then once you have that condition, or you're sufficiently close to that over the range of conditions that you plan to operate the array, then you can choose the source voltages, assuming that there's no mutual coupling. Right? Now this is clearly wrong, but you could start off by doing that and then see how it worked out. Right? So you could see what happens when you make that choice. You find first that the applied voltages are just 1/2 the source voltages for the reasons I just explained. You can now apply the mutual coupling, which would give you the pattern directivity. Now note that we are acknowledging here that there's going to be an approximation in the calculation of self and mutual impedances here. But nevertheless, they're going to exhibit approximately the right behaviors, at least with respect to the variations in the source voltages. So this is a relatively robust thing to do. Then the next thing we can do is compute the actual active impedances. In other words, now that we have the currents, we can figure out what the active impedances are. And from the active impedances, we can calculate reflection coefficients at each one of those ports, given by the active impedances and the source impedances. And from that, we can figure out the impedance match efficiency, which would then tell us how much power got transmitted. And we could also compute the VSWR, that is the voltage standing wave ratio, which is a measure of how much power is reflected from the terminal due to the mismatch that occurred because Z sub n is different from Z sub naught. The differences between these two procedures, which I've identified as A and B here, combined with the approximations built into B, this creates a lot of confusion in practical work. If you're involved in doing this kind of work, you need to stop and think at each point in the exercise what it is that you are doing, what assumptions you are making, and what path you are on. And I would say the most common error is to start off with a formulation like this, or start off using this procedure, and to forget that this is in fact making a pretty bold assumption here about the nature of the active impedances. I'd like to conclude this lecture with two final ideas. One is scan dependence. So we've seen above that the active impedances depend on the currents. That's what makes these kind of unusual as impedances. They depend on the stimulus, unlike most impedances like self-impedances and mutual impedances. So since those active impedances depend on the currents, and the currents depend on the beam pointing direction, right? You'd select those currents to force the beam in a certain direction. Then the active impedances also depend on the pointing direction, which means in turn that the reflection coefficients, the impedance match efficiencies, and the voltage standing wave ratios all depend on scan directions. Said differently, if you follow either one of these procedures to scan the beam in some direction, you will also find that the power radiated by the antenna and the reflection back to the source will depend, that is, vary on scan direction. It will not be a constant, it will certainly vary. So furthermore, it is possible, and in fact common, to find that the reflection coefficient gets very close to 1, the impedance match efficiency gets very close to 0, and subsequently the VSWR gets very close to infinity in some scan directions. So for particular choices of array design and particular scan angles, you end up finding out that this array can't produce any power. It all gets reflected back to the sources. So this is obviously not a condition you want. In fact, you don't really want to be anywhere near this. You want as much power as possible to be transferred from the transmitters to the wave which is created by the array. When you run into this case where you see that the reflection coefficient is getting close to 1, and as a result you are unable to actually pump any power out of this array, that condition is known as scan blindness. And that's obviously to be avoided. So a big chunk of the effort in designing, in particular large arrays, is trying to avoid these conditions where you are either scan blind or you are getting close to scan blindness, because if you're close to scan blindness, you are certainly not efficiently using the power being provided by the transmitters. The second idea is broadbanding, and that's the following idea is that above we've represented mutual coupling kind of as an impediment to the analysis, right? Something that complicates the analysis. But it doesn't necessarily need to be a bad thing. In fact, you can exploit mutual coupling to creatively manipulate the active impedances in such a way that you can increase bandwidth. The change in active impedance with scan direction is inevitable. But knowing that, you could take advantage of the way the active impedance changes and use that to increase the bandwidth of an array. And this is a common effort in designing large arrays. In fact, if you don't consider this at all, you typically end up with antenna arrays that have very narrow fractional bandwidth, maybe on the order of a few percent. If you want a large array that's usable over fractional bandwidths of 10% or 20% or 50%, you typically need to do this kind of thing, exploit the mutual coupling in order to increase the bandwidth. That concludes this lecture on mutual coupling.